All right, in this work example, we're going to be doing some vector addition here. You may recall there was an essential question last Friday about how we can use vector addition to study the effects of wind on the motion of an aircraft. And here's a problem to sort of work with along those lines. You may recall your quiz from last Friday looked like this, right? We're kind of dealing with a similar problem, aircraft going this way, wind going that way. So very similar problem. We've got an aircraft going due north 250 meters per second. And then we have wind blowing at 36 meters per second. It looks like from the northwest, right? 45 degrees there. Draw an arrow on the figure to show the direction of the resultant velocity of the aircraft. So the first step would be to, I think it's easiest to translate this vector this way, to put it head to tail with the first one. So it kind of looks like that. So your resultant should be a long arrow that kind of goes like this. Let me make it clear that the resultant velocity is r. Since I moved my wind vector there, that's my wind vector. This is my resultant here. Okay, so one mark for an arrow that points like that. Chris.
So what I done was pretty much the exact same thing, except I had my the arrow I created match the same length as the aircraft.
You don't really have to draw this resultant to scale. If you actually sort of measure this out clearly, you can use the scale sort of diagram to solve it. The important thing for this mark is just showing the direction of the resultant velocity. So as long as, you could have drawn it like this. Okay, as long as you drew an arrow that points that way, up and to the right, a little bit more up than right, then you got it correct. Okay. You would have missed this mark if your arrow went that way, or you just connected these, like this. That's the typical mistake, is students will just connect the tail to the tail. These vectors are head to head. And the way that we add vectors is to place them, head to tail. So you could have either moved this vector like, kind of over here, right? And then connected it, but you'll still get, sort of that arrow going that way. It is going to be a little bit shorter than the aircraft velocity because there's a component of this wind we're going to calculate in a moment. That's what we call a headwind. So the plane is sort of running into that headwind there, and that's going to slow it down a little bit in the northerly direction. It's also going to contribute to the west a little bit, right? So let's go ahead and calculate that now. I'll kind of work with the vector triangle up here, knowing that I've already sort of moved it in space like this. So the wind is actually 36 meters per second, and it's blowing at this angle. Because the angle there is 45 degrees, if you didn't already realize this, you could prove it to yourself in your calculator that both the sine and the cosine of 45 degrees, same value, right? Because you're perfectly bisecting that 90-degree angle. So the horizontal and vertical components, or the west and south components of this wind vector, or I guess it would be an east. It's blowing from the northwest, right? So it means it's pushing the plane south and east. They're going to be the same value. So let's save ourselves the trig and let's honor our old friend Pythagoras by just using his formula to solve this thing, right? I think we should be able to do that. If we know that they're going to have the same value, get your eyes adjust there. So let's just call this, I don't know, A, and we'll call this one A. So Pythagoras' theorem, a squared plus a squared equals 36 squared for this problem. So we got 2a squared equals 36 squared. Calculating machine nearby. I guess a good step to a squared equals 18. And then we want the square root of 18. So a equals 4.2. All right. I guess I need to take the square of that. That's not right. That's what we call, all right. That's a bad mark to get on your mark scheme. That means wrong algebra. Okay, you don't want a WA. What's even worse is wrong physics. That's where you're like, oh yeah, F equals MA sigma. And sigma stands for God only knows. Like you just made up some physics, it's just wrong physics there. Okay, so we don't do that. We don't do that in ACE physics. We got the right physics. All right. My bad, class. All right. 36 squared. So this should be 1296 over 2, 648, and then the square root of that. So each one of those sides should be 25.5, let's say, meters per second. That seems a lot more reasonable. So it should be that this quantity squared, times 2 equals, and that's the 1296, which is 36 squared. This is a double check. All right, and so we've got an aircraft going north at 250, but we got some wind pushing back at 25.5. Right? So I know that those two vectors oppose each other. In other words, I'm calculating the net north component of this resultant vector here, right? So it's going to be the 250 minus this south component, which I know is 25.5. Okay. So I've got my 250 meter per second aircraft velocity minus my 25.5 meter per second south component of the wind vector, yielding a total northerly component of 224.5. Okay. There's also a component. Let's see here. Moving to the east, that's equal to the same 25.5 meters per second. And so there's my resultant again, kind of going up like that, right? That same direction. And so now I should be able to calculate a squared plus b squared equals c squared or r squared. Maybe make that a little bit cleaner there if I wasn't writing in pen. All right, I got this in my calculator still, so I'm going to square that. Plus 25.5 squared equals this number. 51,050.5, and the square root of that is 225.9. And so the magnitude of the resultant velocity of the aircraft, I would call it 230 meters per second. Report that to two significant digits. If we were to check the mark scheme on this, I'm almost certain that they would accept maybe 226, if you're within sort of one significant digit, but probably 230 is the best answer for that. As a quick review, anytime you're adding vectors, it's really important to sort of visualize them head to tail, and then just connect the tail of the first to the head of the last. Oftentimes you can get the direction there, and then it's just about, sort of resolving a vector, adding up all of the, X components together, the horizontal components together, adding up all the vertical components together, constructing a new right triangle, and then using Pythagoras' theorem to solve for that.